We would like to take a look at a quite complicated neural networks today, where we have a multiple input parameters. How many? We have a n plus 1 input parameters. So at the first inner layer, we have k plus 1 neurons, whereas in second hidden layer we have m plus 1 neurons, and it just continues to the end. We have all these informations given by the neural networks, and we cannot miss any of them to understand the neural networks and what neural networks is doing. See here, we have all the straight lines again from a previous layer to the next layer, things like this. You see here, so that these are the input neurons to this one, and these are the input neurons and for this one. So we're repeating this process all the way to the last layer, which is output layers. And all these straight line represent linear relationships, linear equations given by W input layer, input neurons plus B, which is bias. I'll say this color again for input, represent input. Okay. Now we're going to take a look at how those neurons in here is calculated. See, we call this layers hidden layer, even though I did not show them here. Let me just try to fix right now. These are the first hidden layers, and these are the second hidden layers, something like this. The reason those layers are called hidden layers because you don't know how the numbers is calculated in these circles. And we're going to take a look at how those numbers are calculated in this lecture, where we're going to see the first neurons here, this one, which is this one. See, A0 and top 1. You know, the A0 means that this is the first entry of the neurons of the particular layers, and top 1 indicates that we are at the first hidden layers right there. So understand these notations right there. And all these neurons are calculated receiving from all previous neurons. Okay, so there, let's take a look at then all these arrows and straight lines. You're going to come here, you're going to receive from all previous neurons or previous layers here, something like this. And how many arrows is being received by these neurons? Going to receive n plus 1 arrows here, so they're going to have n plus 1 terms from previous layer. As you see over there, this is n plus 1 terms starting 0 here and all the way to n here. Okay, so these are the n plus 1 entries. Okay, and if you take a look at that, this times this times all the way here, this times this times this times that. So we're going to have all the input parameters is being multiplied as your arrows going down, which are towards the first neuron of the next first hidden layers, as you see over there. So A0, A1, A2, AN, and then you have bias. So this is also shown in the matrix formulation. This times this, this times this, and this times this, and you add a bias. And this is what you can get in general mathematical expressions as you see over there. The problem is to understand then the notations of the subscripts for weights here. Okay, we have two indices to describe the weight right there. The first one and second. First one indicates the index, where the arrows is going to, which arrows it is going into. For example, this one here, the first one. Let me see the first one here. Erase it. The first one here, this one. This one goes the first neuron of next hidden layer, which is 0. So this should be 0 here. 0 here. 0 here. And the second index indicates just where that arrows is originated from. So this arrow is originated from the first one, which is this one right there, which indicates 0. Right? So this W, so should be this W should be omega 0, 0, and indicates from input layer, which is by 0 again, that superscript, so that the first weight is denoted by 0, 0. Can you see? See there, 0, 0, right? So this is what you see in the first ways. Whereas, let's take a look at this one then. How are you gonna denote this one? How are you gonna name this one? See here, we are heading towards the first one again. So the first one is denoted by 0. So let me see. Let me erase this. The first one, we are towards 0 again, and we are originated from 0, 1, 2, 3, 4. This is 4. So it's going to be 4 right there. So this weight is indicated by 0 and 4, and 0 and 4 is multiplied to this input parameters right there. Okay, where we see here, where we see 1, 2, 3, 4, this probably quantity, right? Let me see one we have in the expressions, for example, this one, third one. Let me erase this one and go see third one, he said. So how do you denote this one? This is again the same. See, we have here W, and we are going towards first one, which is indicated by 0 index, so 0, and we are originated from second input parameters, which is 2. So we denote this by 0 2 times. This is the input entries for that linear relationship. So we multiply this by this, get and added one of the elements for this. So this is shown over there. This is shown over there, isn't it? Let me try to erase it. Try to keep clean. Here, this one, right? So in matrix form, it's going to be something like in here and in here, right? So the first neuron or first hidden layers is obtained by adding all n plus 1 entries, as you see in here in mathematical expression and in here in matrix formulation. So there are again calculate multiplying this by this, multiply this by this, and all the way this by this, including n plus 1 entries, and this is shown right there. Okay, and what about next neurons of next layer, which is this one, Okay, let me just try to see how we're going to calculate this one. Then we have to see new arrows towards the next one, which is we're going from here all the way, all the way, okay, all the way. This is the definition of the neural networks, and this is sigma. We say sigma, right? So in order for us to carry out that calculations, we need to first of all define the indices for weight, which is very straightforward right now because we know what's going on there. So we're going to erase this and let's take a look at W. What about this? We're going to take a look at one example, the first one. So first one, we choose now 1 instead of 0 here. So we're going to go 1, 1, and from originated from the 0. So the first entry is based on this weight times the first input layer, which is shown right there. Okay. What about the last one then? Let's take a look at the last one here. We're going all the way from your long journey, and this. Okay, now take a look at the last arrows right there, which is coming from this neurons, this input neurons into this output neurons, and this is very easy to take a look at and determine the index indices. Here, this arrows is coming towards right there, which is the second neurons, which is denoted by 1. So that we're going to have a 1 over there, because this one indicates where our arrows is going towards, and the second index indicates where our arrows is coming from, which is from the last one, which is n. So that the weight over here is indicated by 1 dash n, and multiply that by the corresponding input parameters, which is right there. So that this times this is the last entry probably for calculating numbers in these hidden neurons. And here this is indicated right there, this one. Okay, and then we're going to add another bias there for this second entries, which is A1 and 1. Okay, where we have right there this times this times this times this, and this times this, and we are having a same entry expressed in matrix, where it is more systematic to write down these rules. And sometimes it is more convenient to use a matrix formulations, because matrix formulations helps us to think more systematically, try to avoid any possible mistakes, errors in formulating such a relationships. But these expressions can be it is not difficult, but it is easy to make a mistake because we have to deal with so many indices right there, top and bottom. But the matrix formulations try to make us think systematically so that the error can be minimized. So I recommend this one, actually, you guys. Okay, so I recommend the matrix formulations. So in the similar way, we can repeat all the entries here in output entries right there. For example, here now we have shown how these two circles are calculated, and we can go proceed with all the rest of the circles until the last one. The last one shows here, actually this one, right? Let me just see the last arrows for helping you understand thoroughly again. Let's take a look at this one. What is the W indices for this one? Let's say it is towards this one, right? So this is a K. We are towards K, and the first entry should be K then, right? And then where? From this N. The second entry should be N, because the arrows is originated from, start from the last entries, which is denoted by N, times this entries right there, this one. Okay, this one is the last entries that you have to multiply to this weight, which is a n to top 0, right? This one, isn't it? Okay, so I'm sorry, this one, right? So we're talking this calculations over there, which is given by this and this, right? Okay, and we're gonna add bias as well, and I'm gonna summarize the last entries. This times this times this, and all the way, and this times this. This is what you see over there, right? In these entries, and this is the last entries of neural value for first hidden layers, and also and in matrix form you can get this one. Okay, so I will say that this is matrix form, could be arranged in matrix form, and as I say, I recommend matrix formulations because to avoid the errors. It is very confusing when you have very thick neural networks. We'll take a look at similar calculation that occurs with a second hidden layers right there. So we are talking this right now, this. Okay, now this is a say this is a output neurons here, and this is output neurons here, and this is input neurons. So that this should be right there, and the first entries, I'm not gonna repeat everything again, but I just try to pick a couple of circles and arrows to make sure that to verify your understandings. And in here, let's say take one here, and let's take one here. Sorry, not this one. Let's take one here. Let's take one here, if we understand correctly. What about here? So the first entry is towards where we're going. This, right? We're going this entry, which is 0, from the 0. So this entry should be denoted by 0, for weights, right? And times the this input entry right there from the first hidden layers. So that the first one is you see over there W11 and A0, but top of the number, which is 1. Superscript should be 1, indicating the first hidden layers. Right? So you from first hidden layers as input, and you get second hidden layers as output entries right there. Okay. So we have here again this times this times this, similarly this times this, and you get all these entries over there with the additional bias term, and that is also denoted by 1. As can occur, you denote the superscript for bias 1 while you're talking about the output second hidden layers. But think of this way, this 1 meaning that your arrows is coming from the first layer. You know, this is how the notations or conventions are made. So it's okay as long as you are consistent with the elevation of neural networks. So it really doesn't matter. And maybe the last entries right there, this one towards M. Now we're talking M hidden layer. In second hidden layer we have M neurons. Okay, neurons all the way changes 10, 20, 30 depending on the neural network engineer. All right, so you are now having a M neurons, so that now you are towards M. Okay, M, the last one is M. Last one is M right there. So you're going towards M, which you should write in the first place, and then from where? From K, which is the last entry, input entries right there. So it should be K here, and that multiplied by this entry, isn't it? Times A K. Here this is 1. So you see this entry right there in here. All right, and you repeat the same calculation. This times this times this, and this times this, and that's what you see over there. This times this. This is a each entry is for calculating the AM at the second hidden layers, and you have, don't forget to add a bias over there. Okay, so don't forget to add a bias which is PM to the 1 to match this here, to match this here. Okay, this is M, so the number of rows of B should be with the number of rows with A, so this should be BM. Okay, then we completed all the expressions both in mathematics and the matrix form, as you over there see, so that this is more systematic to use again the matrix formulation. And take a look at the dimensions, if so, to see if dimensions works. If you see over there, the matrix which occurs between input layers and first hidden layers here, and let's say here I'm going to pick up the red color. So this is Km matrix, K by 1 matrix. This is K by N matrix. This is N by 1 matrix. This is K by 1 matrix. Again, this BK, number of rows in the bias should be the same as number of rows with the inputs right there. So we are now cancel this. We are having a here being matrix which is becoming K by 1, so that matrix size verifies, right? Matrix size verifies. Okay, matrix size verifies. And again, if you take a look in the second matrix formulation right there, you're gonna take a look at again the first size for output matrix here, M by 1, you see, and this is M by K, and here this is K by 1, and this is M by 1. So you go and cancel this, cancel, so we are having here M by 1. So that the matrix verifies with the M by 1 sizes for all all expression for second matrix formulation. See over there. So this is very systematic way, so you shouldn't confuse yourself when you do. Especially I recommend doing with the matrix formulations. So matrix formulations are helpful to follow the rule without too much thinking. But anyway, you're gonna repeat all these matrices all the way to the end. So the computer will perform all the calculation which are very similar without any problems. And okay, therefore the sizes of matrix will depend on the sizes of your input parameters and number of neurons, all the hidden layers and number of outputs here. So one thing we can see over there, actually the dimensions of the matrix, which is you see over there, K plus 1. Okay, see this one, K plus 1. See, K is what? K is just the dimensions of neurons. You have a K neurons in the first hidden layers out there. So K is shown right there. So that your matrix size is entirely identical to the number of neurons in first layers, if you are looking at the first matrix expressions. And if you take a look at the second matrix expressions, then that is also identical to the number of neurons that you're looking at from the neural networks. This is M. You have M neurons, and that's shown in a matrix size, which is denoted by M plus 1, and so on and so forth. So you're all the way here. You're all the way here going. The matrix size is same as the a number of neurons for hidden layers. Okay, So it's easy to check whether your matrix works or not by just taking a look at a number of neurons for all hidden layers. That's the way you should check. But it is obvious from these matrix size verifications.